Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 29, 2026, just 2 days ago. It introduces a new architecture called ConceptMoE that dynamically merges tokens into concept representations to save compute, achieving prefill speedups of up to 175%, while boosting performance on long context tasks by 2.3 points. The paper is titled, ConceptMoE, Adaptive Token-to-Concept Compression for Implicit Compute Allocation. And as we'll see later, the efficiency gains here are quite remarkable, given the minimal changes required to the underlying model architecture. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 lays out the ConceptMoE pipeline. On the left, tokens flow from the encoder into the yellow chunk module, which merges similar neighbors, like tokens 4 through 6, into a single concept representation. This compressed sequence enters the central concept model, which handles the heavy computation much more efficiently because it processes fewer items. Afterwards, the green dechunk module on the right expands these concepts back to the original resolution, allowing the decoder to generate precise output tokens. Table 1 quantifies the specific efficiency gains from this compression mechanism. It lists the theoretical attention costs and key value cache sizes for the baseline versus the 3 reallocation strategies. Focusing on the second row, where the model simply adds more experts, we see substantial savings. Specifically, the attention map computation drops by a factor of r squared, while the memory required for the cache shrinks by a factor of r, ensuring that high performance does not come at the cost of memory overhead. Moving from theory to practice, Figure 2 tracks the actual training dynamics. The first graph on the left plots the loss difference during pre-training. The blue curve stays below 0, showing the model outperforms the mixture of experts baseline. The middle chart extends this to multimodal training, indicating even larger gains. Crucially, the rightmost graph reveals the adaptive mechanism at work. While the overall compression ratio stays constant, the model learns to compress redundant image tokens more aggressively, freeing up compute to focus on the denser, more complex text tokens. So, Table 6 breaks down the final results on the open benchmark. The second column shows the standard mixture of experts baseline, scoring roughly 41 overall. Moving to the far right, the ConceptMoE Loop 8 model, trained from scratch, jumps to 47.3. This configuration reallocates compute by reusing layers, leading to massive gains in complex tasks. Specifically, the math score rises from 38 to nearly 53, confirming that deeper concept processing significantly boosts logic capabilities. Ideally, we want high performance without paying a speed penalty. Well, Figure 5 demonstrates that ConceptMoE is actually much faster during inference. The charts display the percentage speedup relative to the baseline mixture of experts model. In the top panel, covering the prefill stage, the dark orange bars show that efficiency-oriented configurations scale beautifully. As the input grows to 1 million tokens on the far right, the speedup climbs significantly, peaking at over 175%. The bottom panel confirms this trend for decoding, where the same configuration achieves nearly a 117% gain as the key value cache size increases. So, Figure 8 investigates if compression hurts learning, comparing the adaptive dynamic chunk method against a naive fixed chunk strategy. Panel A on the left tracks the training loss difference. The dark blue fixed chunking line stays elevated, indicating degraded performance. However, the orange dynamic chunking line improves steadily, eventually converging to a better loss than the baseline. Panel B on the right confirms this on downstream benchmarks. The orange bars consistently achieve the highest scores, outperforming both the fixed strategy and the uncompressed baseline. Wrapping up, 2 takeaways stand out. Treating every token equally is inefficient, and dynamic compression offers a powerful fix. ConceptMoE proves that by grouping similar tokens, models can process long contexts much faster, while actually improving reasoning on complex tasks. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.